Hi, my name is Dr. Scott Parazynski. I was an astronaut for 17 years and flew on 5 space shuttle missions. Also served as the lead astronaut for space shuttle inspection and repair in the aftermath of the Space Shuttle Columbia accident. Currently, I'm the chairman of the board of the Challenger Center for Space Science Education and am the chief medical officer for the Center for Polar Medical Operations, overseeing screening of candidates that will travel to the Antarctic continent.
Hello, my name is Dina, and I was the EVA officer, the EVA lead for STS-120, and me and my team were in charge of the planning, the training, and the execution for the EVAs that occurred on STS-120.
Hello, my name is Derek Hassmann, and I was the lead International Space Station flight director for the STS-120 10A mission. The mission had two primary objectives. One of those was to deliver the Harmony Node 2 module to the space station, and second major activity was to relocate the P6 truss. The P6 truss is responsible for a portion of the International Space Station electrical power system, and when we docked on STS-120, the P6 truss segment was temporarily located in a central area of the space station truss, and it supported the early activities of the station. As part of the evolving assembly of the station, the P6 truss was going to be relocated from that central portion of the station to the outmost port side of the station. For STS-120 10A, the mission initially, the primary goal was, of course, the Node 2 Harmony module, and that was a common element from the time that I began working the mission in the early 2000s to the time that we actually flew the mission later in that decade. One of the big things that got added as the assembly sequence evolved was this P6 truss segment relocation that I mentioned earlier in the discussion. The Node 2 Harmony module was a critical piece of the assembly sequence because it was the connecting module that would allow the connection of the international partner modules, which were, of course, the last key components that we had on the road to assembly complete. So the European laboratory and the Japanese laboratory both would be connected to this Node 2 Harmony module. So it was absolutely essential in terms of the way the assembly sequence laid out that we were successful in delivering the Node 2 Harmony module. In terms of the P6 truss segment, it was to some extent a standalone element in that it could have been completed on any of the missions toward the end of the assembly sequence. It wasn't tied directly to the Node 2 Harmony module per se, but what we did, we looked at a number of these assembly missions late in the assembly sequence and looked at a place where the P6 segment relocation fit, and ultimately we decided that STS-120 was the right place for a number of reasons. The Harmony module assembly and attachment to the station only required basically a single spacewalk and a lot of internal activity in terms of outfitting the Node 2. But we had time basically. The orbiter that we flew on 120 had the capability to stay on orbit for a significant amount of time, on the order of 14 days. We had a very experienced crew with significant background in spacewalks, as we call them, extravehicular activities, or EVAs. Significant background in robotics, and just a well-rounded, very capable crew. So the fact that we had the time, we had the resources, and we had the right crew to go do it, we convinced the program to add the P6 segment relocation to the mission. Going into the mission, we had a total of 5 EVAs planned, which is more than normal. A typical assembly mission contained 2 to 3 spacewalks, so 5 was a pretty ambitious goal that we had going into the mission. Again, the first three spacewalks were the critical task: the Node 2 Harmony module and the P6 truss segment. The fourth EVA, again as planned going into the mission, was a tile repair demo. So we had the spacewalking crew practicing a tile repair technique that we had developed on the ground, and then the fifth EVA, or EVA 5, was a get-ahead for the stage. And another unique aspect of 120 was that the stage had a lot of follow-on work in order to support the assembly sequence. And because when we docked on STS-120, we docked to the front of the laboratory module. But interestingly enough, the front of the laboratory module was where Node 2 eventually needed to be. So we couldn't install Node 2 during the dock mission where it needed to be to support the assembly sequence because the shuttle was docked there. So what we did was we attached the Node 2 module to a temporary location, and then once the shuttle undocked, the increment crew that stayed on the station would then use a robotic arm to relocate Node 2 to the front of the lab. Once we were in that configuration, then we could support the assembly sequence. So I think it's important to understand that 120 was unique in that we had the 5 spacewalks planned during the mission, but we had 3 additional spacewalks planned during the increment prior to the next assembly mission, all of which had to go as planned in order to continue the assembly sequence as it was currently planned. So a very ambitious mission with a lot of content, a lot of things that had to go right. The preparation for the relocation was actually started on a previous mission, on the 12A.1 assembly mission. And as part of that preparation, we had the EVA crew support the retraction of the solar arrays on the P6 segment. So the P6 segment has 2 solar arrays that, of course, produce the electrical power that's then routed to the rest of the station. And we retracted and stowed those arrays during 12A1. As part of that process, the majority of the retraction went very well, but the plan was to retract completely and then essentially latch those arrays down and close a protective cover that would ensure that those arrays weren't damaged during the relocation on 120. And as part of that, one of the 2 arrays went in the box without issue. The second array required a little bit of coaxing by the EVA crew, and we had some challenges getting it to the point where we could actually latch it down and then close the box and button it up and prepare it for the relocation. Based on the reports from the crew and the video that we got on the ground, nobody thought that the array was damaged, but it did give us some pause that it was as difficult as it was to actually get the array back in its box. So the solar array was something that we talked about leading up to 120. We knew it was one of the critical tasks that we were going to have to accomplish. So we talked about a lot of the ways that we would assist if we needed to via the spacewalking crew, a lot of the ground techniques that we could use to help to get the array completely deployed. So it wasn't a complete surprise to us when we had an issue on 120.
STS-120 was an astronaut's dream mission. It was certainly one of the ones on the assembly sequence that I dreamt of becoming assigned to, and was thrilled when I finally got on the mission as the lead spacewalker, because it was all the best parts of EVA and robotics wrapped into a single mission. We were assigned to deliver the Node 2 Harmony module to the International Space Station. It's basically a module with radial ports where Japanese and European laboratories would subsequently plug into. So there was all the outfitting of that new module, and then secondarily, we had to relocate the P6 solar array truss, which had been brought up to the International Space Station during STS-97, I believe in the year 2000. So it had been up in space, functioning for 7 years by the time we arrived. And so we were going to unbolt, disconnect, and relocate using robotics and EVA this large solar array truss and put it out at the very tip of the space station, as far as you can go, further than we'd ever been. And so to get a chance to see the very top of the space station during our initial spacewalks, installing this new module, and then plugging back in this P6 solar array truss, it was a dream mission. And it began flawlessly. We were able to install the Harmony Node 2 without any hitch whatsoever. We were able to disconnect the P6 truss. We had a little bit of difficulty with some of the fluid connectors, and historically they've been very difficult. And on the third spacewalk, we had bolted together the P6 to the P5 truss. We had reattached all the electrical connectors. And I vividly remember coming back into the airlock, and Doug Wheelock, my spacewalking partner, and I were high-fiving and just on top of ourselves, with excitement because it had gone so well. We had feared that there might be some hiccups along that evolution. But as we floated out of the airlock and flew into the laboratory module where all of our crewmates were assembled, we could see that they were looking through the closed circuit TV system out at the solar arrays, which they had just commanded to extend. And what they saw was really ugly. They saw a solar array panel that had been ripped apart, essentially. It was only partially deployed. And we weren't sure the reason for the damage, but we knew that it wasn't going to be possible to continue the extension of the solar array, and some real trouble shooting was going to have to take place on the ground.
At the end of EVA 3, with the crew heading back into the airlock, the team on the ground and the crew on orbit, everybody, and the engineering support in the control center, everybody was feeling really good about how things were going. And I remember, the array deploy was initiated by the crew. It was going well. The Falcon operator, the electrical power specialist in the control center, was monitoring that array deploy, and my focus was on getting the EVA crew back into the airlock and then getting them back up to pressure and, of course, out of the suits to complete the EVA. And there was a period where we didn't have video downlink, which is typical. We have periods of video outage normally on the station. And I remember the video coming back on the big board in the control center, and there in the middle of the screen was a close-up shot of this solar array with a very, very ugly-looking tear. So at that point, I realized pretty quickly that the mission, as I knew it, was probably over, and that our focus was going to change significantly. And one of the real challenges of all this was that because of where the solar array was on the station, so far away from the cluster of pressurized modules where the crew lived and worked, was that it was very, very difficult to get any kind of good idea of what exactly was going on. The tear itself was actually a tear of the hinge, not of the solar array itself, not of the array material itself. It was clear that hinge was torn, but there was guide wires that went up and down the array that were also involved in some way in this tear, in this anomaly in the solar array, and we just couldn't get any good close-up video or photography in order to help us understand it. So as we worked through the planning and the build-up to this spacewalk to address the problem, there was always this uncertainty about what Scott was going to encounter once he actually got to the work site. When you have a shuttle mission, you have 6 or 7 crew members that have been highly and specifically trained over the past 2 years minimum to do all of the work associated with the things planned on that mission. So in this case, the 120 crew was experts on the Node 2 module, both the extravehicular activity portions of it, all the work that had to be done during spacewalks, as well as the IVA, or the internal activities that had to be done on Node 2. The spacewalking crew were highly trained on all aspects of the P6 segment, on all the handholds, all the access points, all the no-touch zones, everything related to the solar array. So when you have a highly trained crew there, and you have just a number of bodies that available to throw at the problem, you have the resources on orbit, there's a great urgency in the control center to address the problem before the shuttle crew leaves. And that was another driver for the way we approached the issue with the solar array.
The next 72 hours were a whirlwind, not only for us on board the shuttle station complex, but also, in particular, here on Earth. We needed to provide as much detail as we could to the ground team so that they could figure out, first off, what had happened, and then to give us an idea of what we might be able to go do to fix the problem or potentially jettison $1 billion solar array. To give it some context, this was a partially deployed solar array, so it was very susceptible to any vibrations and loads. So even the thought of undocking the space shuttle at this point was very concerning. Would it come apart? Would it hit the space shuttle, damage the TPS? Would it damage one of the pressurized volumes? So there's a lot of concern, allowing us to even come home in that condition. So it was really incumbent to figure out a way to either go repair the solar array and allow it to be fully extended, or to potentially throw it away. We're also critical to the power on that solar array panel to be able to power the upcoming European and Japanese modules. So it was a do or die period of time on the ground. The stakes were incredibly high at the time of this failure. We had a finite number of space shuttle assembly flights to the International Space Station left. We had a drop-dead date of 2010, I believe. That's when the Columbia Accident Investigation Board suggested that we should not fly the shuttle beyond, because it would require complete recertification, which would have been prohibitively expensive. So we had a lot of pressure on us to get the space station assembled. Immediately after our mission, we had critical missions from Europe and Japan, their laboratory modules that required the power from this solar panel. If we hadn't been successful in restoring power to this array, there might have been rolling brownouts aboard the International Space Station, or they might not have even flown those missions, and that would have been a devastating loss to this enormous investment in our national laboratory as well as an international space station. So the stakes were incredibly high to find a workable solution, not to go out and throw away $1 billion space asset, but to restore the full power of the International Space Station by fixing it.
STS 120 started off as a completely different mission. We had 5 EVAs planned. Our major mission objectives were to install and outfit a new module, Node 2, and also to take a truss segment, which was in the middle of the station, and move it all the way out to the end of the station, the P6 truss. And additionally, we were going to be experimenting with some tile repair goo, we like to call it, but basically some ablative material that we could use to repair tiles on the shuttle, should we have some sort of an issue like we had on Columbia, but on the tiles. And so we were really excited going into the mission. We already had a really, really exciting mission planned. And then as we started into the first and second and third EVAs, everything was going pretty well, but we wanted to examine the solar array rotary joint on the starboard side. It had been vibrating some when we were rotating it, so we sent the EVA crew out to go look underneath one of those covers on the solar array rotary joint, and we saw a bunch of metal shavings, filings, and we knew that wasn't good. It was supposed to be clean. And then on the third EVA, we went out and looked at the port side on the solar array rotary joint, and it was pristine. So our team started planning a very large EVA, which was going to be meant to substitute for one of the 4th or 5th EVAs, and this was a solar array rotary joint cleaning. So we called up what's called Team 4, a really big team of people, led by a flight director, but including all the engineering management and teams and all the safety teams. And that team had started to already develop and completed the development of an entire spacewalk to go out and clean that solar array rotary joint. By the time EVA 3 came around, when we were going to deploy the solar arrays on P6, our team 4 had already been developing this big EVA, and were pretty much had expended a lot of their energy up to this point. And then when we went to go deploy the solar arrays, one of the solar arrays ripped on P6, and we knew right away, looking at that might change our whole game plan. So the context is, maybe going into the solar array repair, already we had put a lot of obstacles behind us, we thought, and now we had another big obstacle in front of us. It's kind of a risk trade. We knew that we didn't want to undock the space shuttle with the array torn, and we knew we really didn't want to dock another shuttle with the array torn. We weren't sure what the behavior was going to be with the array. So somewhere in there in the program, we knew we were going to have to fix the array, and this was really our opportunity. We had an excellent EVA crew on board, and we didn't really want to put ourselves in a risk posture, such that an unknown structural configuration with the array upon docking and redocking. So we knew that suddenly we had kind of a game changer on our hands in the middle of the mission. At this point, as we're changing our mission around, we need to go from work on the SARG EVA to work on the solar array EVA, and we already had a lot of the Team 4 players in place. So we had a lot of the same people that were the electrical power system folks that were associated with the solar array rotary joint, and then we're also associated with the array. But I think that maybe we had to double or even triple the number of people that it was going to take to fix the array over what we had already been working with the Sarge. It took pretty much every available hand to go do that. The way the EVA was designed was that Scott Parazynski, we'd put him on the tip of a boom, and in the center we grapple using robotics, the station robotic arm. We would sort of thread the needle and send him out to the very, very end of the solar array, or I should say the end of the truss near the base of the solar array, to allow him to enact the repair. And so now this team had a new focus. There was a lot of risks associated with doing that type of repair, including getting there, which included the robotic piece and also the just distance. Can we even make it out there? And then additionally, we had the challenges associated with working on an array, a live array. You can't shut the arrays off. We had a lot of risks associated with that the team had to go weigh. So the team had to really change direction and focus quite a bit. But luckily, I think we had a lot of the experts kind of already working on the Sarge problem. So there we were. We saw that the array was torn, and we knew we were going to have to go off and do something. So Team 4 got together again, and that process is, Team 4 and the console teams, they work hand in hand. And so I was the throughput basically for any training for Scott and Pam and for anyone on board, and all the procedures and everything that the crew was going to execute or see. I was the one that was, my team and I were the ones that were getting all those materials together and uplinking those to the crew. But off to the side, Team 4 had gotten together and had started the process again. They went out to Building 9. Building 9 is a place where we have a lot of markups, and we happen to have an engineering wing, a solar array wing. Pre-flight, Scott, I trained Scott on all the different locations he could and couldn't touch, but we knew that he wasn't going to remember all those details from pre-flight training. So we summarized again everything that we wanted to make sure he remembered. The team went out on Team 4. They went out there and they specifically talked about the array. And the team also developed this cufflink, which was essentially kind of like two bands with a string in between. And we were utilizing the holes in the solar array wing to stuck those together to bring the array into one piece rather than the ripped portion that it was. Additionally, we had to pick apart a big snarl of some wires. And from that, we were really trying to come up with a concept that Scott could use for anything that he saw there, because we didn't have the detailed pictures that we'd wanted to have. In the end, it was really a matter of taking some needle nose pliers and making sure that we understood how to cut or to pull in certain areas, and then just sticking the cufflink in. But all of that required a lot of work on the ground to make sure we understood what we could and couldn't do in terms of touching and not touching, come to agreement with all of the different electrical folks and safety folks who understood all the different risks. So there was a really big movement afoot, and a lot of that happened off console, not in mission control, as I said, in the Team 4 area. And then Team 4 would tag back up with us, and then we would relay crew questions or concerns from my console back to them, and we had kind of a nice symbiotic relationship.
In terms of the risks we were looking at, there was risks on a number of levels. First, from a program perspective, it became obvious pretty quickly that we had a potential of a significant impact to the assembly sequence. And this was, if you recall, this was late in the assembly sequence. We had a handful of missions left in front of us, and everything from where we were on 120 to essentially the end of the shuttle program, the completion of station assembly, was very serially planned, tightly choreographed, and had to go as planned in order to support the end date that we were working towards. And early in the program, we were much more equipped to deal with something like this, because, as an example, we could have dedicated the next shuttle mission to addressing the issues that we had with the solar array. At this point in the program, where we were in 120, we just simply didn't have that luxury. We had a finite number of missions left in the assembly sequence. All were tightly packed with activities that had to happen to complete the assembly sequence. So there was a significant urgency on the part of both MOD, the Mission Operations Directorate, and the program to do whatever we could during this docked mission to address this solar array issue. And there was also a very near-term issue in that there was uncertainty about this, as I mentioned before, about the structural stability of the array. It's likely that we could have gotten comfortable undocking the space shuttle with the array in this partially deployed configuration, but there was uncertainty about what impact that would have on the array. Would it do additional damage to the array? Would it increase the size of the tear? Would you get actual damage to the other portions of the array? There was just people weren't at all comfortable doing the undocking with the array in this configuration, and because of the nature of the failure, there was no real option of going back or forward. We couldn't retract the array and put it back in the box clearly because of the torn hinge and this tangle of guide wires that we thought we saw, and we clearly couldn't continue with the deploy again for all the same reasons. Everybody was certain that if we tried to retract or deploy, we were going to make the problem worse. So it was important to everybody involved that we get this addressed before we undocked. In the case that we undocked in this configuration, docking, the next shuttle docking was even more of a concern because there's greater loads associated with it. Again, with the Soyuz and the Progress dockings, those loads are typically greater than shuttle loads. So the uncertainty relative to the structural stability of the array was a big driver and the biggest program risk really associated with this the issue that we had.
This particular EVA has a lot of risks associated with it that is not included in a standard EVA, and a lot of the risks are associated with the array itself. So as I mentioned, you can't turn an array off, and so we, in order to avoid the risk of electric shock, we had to put a lot of mitigation strategies in work, including working on the backside of the array. We had to tape Scott's the wrist rings. That was an area where he could get close to the array. We didn't want to have any arcing or sparking. The tools, we taped a lot of the tools up, and we tried to keep as few tools on Scott as possible so that there would be no risk of inadvertent contact of any of the different tools. And of course, the risk that you're trying to mitigate in this case is electrocution, but it would take quite a few failures, if you would, by the time we had all these mitigation strategies in place before that could occur. And also, of course, he's working in a pure oxygen environment, so you wouldn't want to have any arcing or sparking in the inside the suit. We also had a molten metal risk where we were worried about if we had any kind of a metal tool contact the array in a specific location, you could get a droplet of molten metal that could land on, for example, his glove and then cause a hole, and which would cause a leak in the suit. Additionally, we were worried about sharp edges. The arrays were not really meant to be EVA handled, and so there were sharp edges all over the place. Additionally, we had the array was broken, obviously, and torn, and so we were worried about what we couldn't even see. One of the major situations we were really watching was the number of dock days that we had. We wanted to make sure that we on this EVA, that we conducted this EVA while we were docked, if possible, and we did have a limited number of dock days. So I think one of the major mitigation strategies, though, that our management and the flight directors used was trying to figure out what was the best day to conduct that. We ended up having to cancel the SARG EVA, and we also delayed this EVA by a day, all to make sure that the team was really prepared and focused and ready to go out the door, the team and the crew, by the time this rolled around. So we weren't still worried about the SARG EVA. They took that off our plate. And they also gave us an extra day when it seemed like maybe everything hadn't completely come together yet. So there was a lot of mitigation strategies throughout associated with both the details of the EVA and where the EVA was placed. I think from an overall risk perspective, the very large team understood that something really needed to be done with the array. This wasn't mission success. This was what's going to happen to the array when we undock, what's going to happen when we redock. We aren't sure. So something's going to have to be done, and we were going to have to figure out what to do, and EVA is the obvious solution there. So then I think the team took the balance of just undock and redock with the array as is, which is highly risky, and they said, well, if we were going to go do an EVA, what could we do? And we took that and put it into little chunks. And we said, well, we'd have to get close to the array. Therefore, we need this mitigation, this mitigation, this mitigation. Can we do it? We have to somehow get out there. We have to put Scott on the boom. Are we able to do that? And so we kind of looked at each and every piece, and the elements all came together. And I believe that our safety organization was extremely helpful in this situation, because none of us, from an EVA perspective, or the robotics, or the flight director, or the crew on orbit, none of us were electrical experts in what kind of voltages would cause electrocution, those types of things. Our safety organization was able to root all that out. I do remember having a moment where I said, I need safety here right now. And a member of my safety organization came and sat down next to me, and we went through every one of those risks I talked about: molten metal, electrocution, sharp edges. We talked about every single one of those things and what were all the mitigation strategies that we absolutely had to do, and I had to make sure that my team incorporated in the procedures. And I felt really good by the time the EVA rolled around that we had everything in place that we needed to go do.
Going into a shuttle assembly mission like this, or in general, what we do in the Mission Operations Director, we get input from the program on priorities. And the program tells us, here's the list of things that we want to accomplish, and here's the priority order. Of course, in our case, the priority was the Node 2 module, the P6 relocate, and then essentially all the other tasks that we had included in these 5 planned spacewalks. And as part of the planning process, we in operations look at the pinch points, the critical parts of that sequence, think about how they might go poorly, and then talk about how we would react if those things happen. Once we document those pre-planned decisions in what we call flight rules, we then have the program review those rules and concur with operations that that's the right course of action. So in general, with the nominal timeline going into an assembly mission such as 120, we'll have the nominal timeline laid out. Here's the sequence of events if everything goes well. And typically we look at the critical failures so that if X happens, then our response in operations is Y and Z. So that we don't have to have a lot of real-time discussions with program management, with engineering, while you're wasting precious time with the shuttle on orbit. So because you have that finite time that the shuttle can stay on orbit, it's very important that we talk through all the potential issues, or all the potential issues that we think are worthwhile and credible. Discuss those with the program, discuss those with engineering, all pre-flight, have those decisions canned and ready to go. In the case of the 120 solar array tear, this particular failure was not one that we had talked a lot about pre-flight. And quite honestly, it's not that it wasn't credible, but that it was a very difficult failure to address, in that we had the partially deployed solar array. So without the analysis on the structural stability, it was very difficult to define what the right course of action was. So, it was clear to me once I saw the tear that we were going to have to call in additional resources. And one thing that we've done over the years in the Mission Operations Directorate, we have 3 teams assigned to any given mission. We have 3 shuttle flight control teams with associated flight directors. We have 3 teams on the station side with an associated flight director. So as an example, on the station side, I was the Orbit 2 flight director, and then we had an Orbit 1 and Orbit 3 flight directors. We also have what we call a Team 4 assigned pre-flight. So we have a Team 4 flight director, and then we have a Team 4 representative from all of the flight control positions, like the electrical power, thermal control, guidance, navigation, and control, computer systems, etc. So we have a separate and 4th off-console flight control team that doesn't have normally assigned duties for the mission. We also have representatives on that team from the program and from engineering. So they are there. This Team 4 team is in place pre-flight to address situations exactly like the one we had on 120. If there's going to be a significant amount of off-console work, development work, analysis, conversations with the program and engineering, that's exactly the job that this Team 4 conducts or supports, while the assigned teams in the station and shuttle flight control rooms continue to do their job. Because as folks are figuring out how to address this solar array tear, life goes on station. We've still got a lot of work to do inside the space station in terms of transferring items from shuttle to station, transferring items that are going to come down from station to shuttle. We carried up a number of replacement units for hardware that had failed in the station. So the crews stayed very busy inside the space station doing their normally planned work while Team 4 did their activities leading up to the EVA.
Several different teams were assembled in very short order. A Team 4 mission control team was set upon this to, first off, figure out how we might be able to get an astronaut out to the very tip of the space station to do a repair and to develop a robotic trajectory to fly some sort of platform out there. And what they came up with was the combination of the space station's robotic arm, Canadarm2, grappled to the midpoint of the OBSS orbiter boom sensing system inspection boom in a way that had never been envisioned prior to the mission. We always wanted to keep that thing unpowered for the shortest period of time possible so that we wouldn't lose the ability to use those laser sensors on the tip of the boom. But this is a reason to take a little extra risk with those sensors because we needed to get someone out further than we had ever gone before on a spacewalk. The other parts of the team were looking at, well, what do we do once we get out there? Can we remove a guide wire that we assumed had become frayed and had ripped apart the solar panel in a couple of different places? So we had engineering hardware in Building 9 here at the Johnson Space Center where people came up with different solutions, including the development of this very clever piece of gear. This is what ultimately was called a cufflink. And I love this. It's made of 12-gauge wire, and we had aluminum shim stock aboard the International Space Station, so a couple of little tabs were built into the tips of these wire bundles. And the idea was to take advantage of the alignment holes that were built into the solar panel for launch. They're little posts that the panels, as they accordion down onto the bottom of the blanket box, they would align the panel. Well, we wanted to, first off, go out and cut the frayed guide wire that we assumed was there, and then bridge the gap. So to pop one of these in above the damaged site and one below, and then allow full tensioning of the solar panel. And so, as simple as that sounds, it's quite complicated because of the reach and access involved, and then of course the fact that this is a fully energized solar panel. You can't turn off a solar array once it's up in space. Even Earth glow causes some energy collection from the solar panel. So the whole approach to risk had to be shifted a little bit. We had to accept a little bit higher element of risk because the rewards were so important.
In terms of lessons learned or things that I took away from the 120 experience, one of the primary lessons learned for me, or one of the things that was confirmed for me, was how absolutely essential this concept of a Team 4 organization is in order to address a situation like this. Because the reality is, if you have an issue, a challenge, a failure, life goes on in the control center. You've got on the order of 13 crew members on orbit who have assigned tasks. You have ongoing activities that need to happen separate from the spacewalks. So the three teams that are actually doing the work in the control center are fully loaded. They're doing everything they can to keep up with the normal timeline. And it's also very, very important that team goes home when their 9-hour, 10-hour shift is done, because the tendency of the dedicated folks that we have in operations and engineering across the program is they're going to want to stay. And if there's this tremendous workload associated with this other problem, the tendency is for them to stay much longer than they should. Then the next shift, what you have is a poorly rested team not performing at a peak level. So this Team 4 concept is absolutely essential in order to get the work done in a complete, comprehensive fashion, while allowing the normal teams to do their job at the control center and to get the rest they need. One of the things that I personally was worried about in a situation like this is just the number of hours that folks are working, because my Orbit 2 team was assigned to the mission for almost as long as I was, and of course we worked through all the planning and all the training to build up to this mission, and people have an emotional attachment and a commitment to making things work, and there's a huge amount of personal responsibility when you have just in general to the mission, and then when you have a situation like this that puts the mission at risk, certainly you can see the commitment and the attachment that people have to the success of the mission. So one of the things that I wanted to guard against, and I warned other folks about, is just the amount of hours that people were working. It's just so important that you not let yourself stay at the control center 24/7, because the reality is you've got another shift coming in about 16 hours or less, and it's important that you be at a peak level of performance to support that shift. And so I talked to my team on multiple occasions about the fact that we need to do what we can as the Orbit 2 team to help Team 4 be successful, but make certain that as an individual you recognize the point at which you've done what you can as the Orbit 2 flight control team. You've equipped, you've given the Team 4 folks what you can during the period that you're assigned to be there, and then go home and unplug, get the rest you need so you can come back refreshed the next day. And you know, I think we were generally successful doing that. I know that the most probably clearly the highest loaded organizations or positions were the EVA console, or the folks responsible for conducting the spacewalks. They were designing the spacewalk from scratch, and the robotics flight control position. They were building all the robotics procedures from scratch. So those were the most heavily taxed console positions in teams, and those are the folks I tried to keep the closest watch on in order to make sure that they were doing what they needed to get us to the spacewalk, but also to be well rested and prepared for the next shift, and eventually for executing this highly critical spacewalk.
We had a fantastic, harmonious crew. Everyone was, I think, during this whole evolution, firing on all cylinders, and everyone had an important role to play. Of course, we had a space station commander who was Peggy Whitson, and a space shuttle commander, Pam Melroy. But we had other leaders of other activities. I, of course, was the lead spacewalker. Stephanie Wilson was the lead robotics person. But it didn't really matter what leadership title you had. All of us felt empowered to say, this is not safe, we need to knock it off here. Similarly on the ground, Derek Hassmann, who is our lead flight director, Dina, Contella, who's our lead EVA flight controller, Sarmad Aziz, the lead robotics officer. Everyone was watching different data sets, and as you know, at varying times people have different levels of situational awareness. And so what I may have in front of me in my tunnel vision world may not be the full picture, and maybe something that Doug Wheelock saw beneath me, or that Sarmad Aziz on console or Derek Hassmann saw in Houston would necessitate waving off. And so we were very prepared at any point in this to go to Plan B or Plan C.
We did have several lessons learned on this mission. One of the lessons learned from my perspective is related to EVA guidelines. So, for example, we had a 30-minute time to airlock that we've always used as a guideline. Crew members shall not go out so far that they can't get back to the airlock in 30 minutes. And this is based on a certain size hole in a suit, in a particular suit leak case, and that determines how much oxygen you have. And I think, we've used this as a guideline, and anytime we break this guideline, then we have to have a big conversation about it from a safety perspective, and is this the right thing to do? And from a mission success perspective, we generally did not break this guideline. In this particular case, we had risks to our crew, a risk to our overall station and shuttle programs, pretty big risks associated with this torn array. And so in this case, we had to really examine this 30-minute guideline that we were using to decide, is this really the right guideline in this case? The 30-minute guideline, like I said, is based on a very specific size hole, so it'd have to be a very specific kind of failure, and we haven't had one like this in the past. So in this particular case, we explored what would be the quickest ways to get back to the airlock, and we made sure that we really had to go to handle on all those things. But in the overall risk trade case, we did balance that particular risk with the risk of undocking or docking with an array in an unknown state. So robotics played a really big role in this particular EVA. Scott had to get all the way out to the end of the truss and then up some to the array. And the array failure occurred in a very smart location such that we could just barely get to it. If it had been even just a little bit higher, then we would not have been able to repair the array. And Scott's a pretty tall guy also, so we put him on the end of the boom, and then we used the space station robotic arm to put him out as far as the arm could possibly reach. And as I said, it was just barely reaching, and it was very difficult from a planning standpoint. The arm, once it gets all the way straightened out, it loses a degree of freedom, basically. And so the robotics officer and myself and the flight director were all extremely concerned that Scott was not going to be able to make it there. And I recall one tense moment where Scott was asking, I just need a few more inches. And the robotics officer's like, well, I can't quite straighten the arm anymore. And so we had to have quite a bit of discussion about how we were going to exactly get Scott there. And in the end, of course, the robotics officer and the crew on orbit were able to figure out a way to get Scott there. Well, in this particular case, the robotics and the height of the crew member and the skills of the robotics folks on board and the skills of the robotics folks in the control center, all of that kind of came together to get Scott right there. And I don't think that if we had had that preparation and that capability and that willingness to drive to go just a little bit further, then we would not have been able to do the repair. The lesson associated with robotics and also with EVA is really just to remain positive and think that you can go do this. I believe that there are folks in the robotics camp, the EVA camp, the safety camp, and all these different camps. There was an occasional kind of worry that maybe we wouldn't be able to do it. And everyone in the real-time environment, the crew and the console team and a lot of the engineering folks, and there was a lot of people that thought we could do it. We just had to push the envelope just a little bit. So the lesson is really to try to push the envelope. And if you can't do it, that's okay. But as long as you're just staying inside the safety box, you're not getting in an unsafe configuration, you should still continue to try to get there so that you can do something wonderful.
One of the risks that we had to accept for this particular spacewalk was the fact that we'd be further away from the safety of our airlock than we'd ever ventured in the past. The secondary oxygen pack of the extravehicular mobility unit, or EMU, or spacesuit, is designed for a small leak and 30 minutes of reserve. So you're out at the end of your rope and you get hit or you have some suit malfunction. This system is designed to give you 30 minutes to get back home. It was 45 minutes one way to get out to the solar array repair site. So we had to think about risk in a slightly different way. We had to accept a higher degree of risk because the rewards warranted it in this one particular case. I don't think you'd want to blindly accept that decrease in margin for every task, but this was a case where we thought that we could accept a little bit higher risk posture because of the consequences of not getting the job done. And we had done some thinking beforehand in real extremis if I had sustained a hit or developed a leak in my spacesuit, I would have done what was necessary, and that might have meant shimming down the robotic arm and not riding a 45-minute trajectory back to the truss. I would have been highly motivated to get back in less than 30 minutes. What you're looking at in this picture is myself at the end of a 90-foot-long robotic assembly. It's the Space Station Canada Arm 2 grappled to the OBSS inspection boom, along with a foot extender, so it gives me a little added reach, and it took my full 6'3" frame to actually reach this work site. Had it been even a foot further away, I don't think we would have been able to have done this repair. You'll also see at the base of the array my spacewalking partner Doug Wheelock, and he was essentially my spotter during this whole evolution. If you were to press on this gold panel, it would actually float away from you like a giant sail, 5 or 6 feet, and then come back towards you. Therein lied the danger, because had it contacted any of the metal parts of my suit, I was at a significant risk of shock. It's a gold, shiny, beautiful-looking structure, but it's actually quite dangerous because it has 100 volts of energy coursing through its circuit boards. On the flip side of the array, it's kind of got a bluish color to it. It's hinged at many layers, as you can see, and it's quite flexible until it's fully tensioned, and then it has the rigidity that it requires to be able to be rotated to track the sun during normal operations. But when we were working on it, the whole assembly was kind of like a limp noodle and required a lot of extra attention.
Another personal takeaway for me in terms of lessons learned was the use of the OBSS, or the Orbiter Boom Sensor System, to support this spacewalk, because we couldn't get Scott Parazynski to the work site, to the place that he needed to be to actually repair the tear with the station robotic arm alone. We needed an extension, if you will, of that arm, and what we did was we grappled the OBSS, the Orbiter Boom Sensor System, with the station robotic arm, and then put Scott at the end of that in order to do the work that he needed to do. And it's an example of having a resource that perhaps you didn't completely appreciate at the time available to you, in that without that boom, it's not clear to me that we could have effected the repair at all, and we might have been faced with actually jettisoning the failed array. And ultimately, we left, once we completed the use of the boom on one of the last shuttle missions, we left the boom on orbit in order to support exactly these type of contingencies. And we actually took it a step further in that we modified the arm such that we have a grapple fixture at the end of the arm, because on 120, we had a grapple fixture at the middle of the arm, and that basically half of the boom was enough to get Scott where he needed to be to do that array repair. But on station today, we have an even greater capability to use that boom to get the crew to places that are significant distances away from normal work sites.
Team 4 is a very large group of people. It's run by a flight director, was involving a huge number of engineering folks, structures, electrical, those sorts of very smart folks, and also a large number of operations folks. I know in my camp, we used every available hand, everybody. Everyone that knew anything about EVA was invited to participate and did, and really contributed. And the difficulty you could have in some of these cases is it might have happened over Christmas, but it didn't in this case. So we had everyone who was around that could help us, and we used every single person. The safety community, I felt, was extremely important in this case because I was not aware of all of the challenges associated with the plasma environment and the voltage on the arrays and all the different ways that a crew member might get electrocuted. The spark would have to jump from one metal piece to Scott would have to be sweaty, and his sweaty part would have to touch that metal piece, and then the metal piece would have to touch another sweaty part. There was a lot of complications in trying to understand what was the actual hazard, and the safety community really brought together the electrical community, the suit, the spacesuit community, and the ops community to make sure that everybody had a good handle on what the hazards were and how we would go about mitigating them. So we really used every available hand, and I think we couldn't have pulled it off if we had not had as many people working on the problem as we did.
One of the challenges associated with what we were trying to do on 120 is that there was a lot of uncertainty about exactly what the issue was. How the array was torn, how stable it was, how these guide wires were involved, what tools would be required to address it, the access, and how new and different it was. Because I talked about essentially a 2-year template of the planning and training leading up to these pretty complicated shuttle assembly missions, and included in that training is quite a bit of spacewalking training, where we put the crew through the nominal timeline in the neutral buoyancy lab, and they do the practice in order to make the EVA smooth and efficient. In addition, one of the challenges of the 120 spacewalk was the fact that the robotics had to be tightly choreographed. So, a spacewalk on its own is challenging and requires a lot of training and a lot of detailed review. But when you add in robotics that have to fit seamlessly within the flow of the spacewalk, that's another level of coordination and another level of difficulty and complexity. So, this 120 array repair was about as complicated and as difficult a spacewalk as we could have mounted or imagined. And we had to do the planning and the validation of the techniques in a very short period of time. So one of the challenges we had on 120 was deciding when we were ready. We wanted to take enough time to make sure that the procedures were exactly right, that all the spacewalking procedures were exactly right, that the robotics procedures were good, that all the activities were safe, that we had the right tools in the hands of the crew. But we couldn't take so much time that we ran out of runway in front of us. In other words, as a goal, we wanted to do this spacewalk and have enough time to do a second spacewalk if necessary in order to address what we learned during that first attempt at the array repair. So one of the most significant challenges that we had was deciding when it was time to pull the trigger, so to speak. And that required that this Team 4 activity to reach a point where the procedures were mature enough to actually give them to the crew. So we had to get all the buy-in from the mission management team, from engineering, from safety, that, these are the right techniques, these are the right procedures, they're safe, and then we need to get that package of information uplinked to the crew so that they could review those procedures in detail and typically send us back a series of comments. So one of my takeaways from 120 is actually how well the system worked, because it was critical that we get all the procedures right, but it's also critical that we do them quickly. So everybody had to understand their role. Everybody had to be supportive and engaged and thinking outside the box, but also, always with the safety of the crew and the vehicle as the paramount consideration. So we would typically churn or work for about 8 hours, reach a point where it made sense to give the crew a status. We'd uplink those procedures to the crew, and then typically in the Houston mornings, we'd have a mission management team briefing where we would give the managers a status. So, I can't say enough about how well the team worked, how all the pieces of the organizations functioned, and then how crisply we got those important decisions from the mission management team. And EVA 3, which was the completion of the P6 relocate and the array deploy, basically the day that we saw the tear, was on flight day 8. We ultimately conducted the spacewalk to repair the tear on flight day 12, and our goal kind of fluctuated as we got a shift of work behind us. Our original goal we thought we could get to with flight day 11. We reached a point in the development process where it was clear that we just weren't ready. The procedures weren't mature enough. The crew wasn't ready. There was issues that still need to be worked. So we actually delayed the spacewalk a day to flight day 12. And looking back on it, it was a difficult thing because you wanted to get moving. You wanted to go fix this problem, which you knew was a significant risk to the assembly sequence. But on the other hand, you wanted to make absolutely sure that the teams on the ground and the crew on orbit was ready to go do the repair. In the lead up to an assembly mission, the template is about 2 years, and during that time, I work very closely with the assigned shuttle crew. I work with the station crew that's going to be on orbit during the time that the shuttle's there. And I also work in simulations and planning with my flight control team. And those relationships that you form in the months and years leading up to the mission are absolutely critical when it comes to a situation like we had on 120. And there's a couple aspects of that. One is the communication issue. Just crisply communicate important, complex topics. And number two, and very significant, is the trust. That each element of the team understands that everybody else is in it to be successful for the mission to be successful, to keep the crew safe, and that there's a trust in your level of professionalism, there's a trust in your level of preparation, and there's a trust that all you want to do is the right thing. And I think on 120 that became extremely important in that we were trying to get the crew rapidly up to speed on these complex robotics and spacewalking techniques in a very small window of time. And it wasn't efficient to keep them updated, for example, hourly. We needed time on the ground to go do significant amounts of procedure development and analysis and simulation in order to get a package ready for them to then review. So there was periods of time, sometimes all day, sometimes 8 hours, where they wouldn't hear anything from us relative to that spacewalk. But, the crew trusted us to make the progress that we needed to make, that we would incorporate their comments and get them a good product. So, I can't say enough about how well that communication and coordination worked. The crew trusted us to build procedures and techniques, concepts that would work. We trusted them to give us reasonable feedback, not make perfect, but important changes to the procedures, updates that we had to make. And the fact that we got there in 4 days is a tribute to the relationships that we built pre-mission and just how well the team worked in real time.
This was an instance where the broader NASA team really pulled together in vital ways. We had, of course, EV experts and robotic experts and ops people on the ground, folks who represented the hardware provider, representing the solar panel team, and then members of the crew office who were helping with the procedure development on the ground, integrating very seamlessly with us on board the shuttle station complex. And we had a number of video conferences where we asked lots and lots of questions, and there's lots of dialogue back and forth, and special requests that we suggested were honored, which is very helpful. One of which was to have a special cuff checklist procedure so that I had visual cues on exactly where these cufflinks would be installed and things that I should look out for. So there's a lot of give and take, and I really had a high degree of confidence that we would be able to do the CVA safely. I didn't know with great confidence that we would be successful in doing the repair, but I knew that we could get out there and have a really solid fighting chance of getting it done. And so one of the lessons learned is when faced with a challenging situation, unforeseen situation like this in the future, is to bring all the stakeholders together along with the crew and evolve the solution as a team. And it was an incredible home run, I think, in this particular instance.
And one of the things that becomes obvious with a situation like we had on 120 was the resources that are available to us in a contingency situation. And the typical example or the classic example is the Apollo 13 example, but we saw something similar on 120 in that if you do have a problem, it's just amazing the resources that we can reach back and tap into. And for 120, we had a range of things that we needed help with. We had the robotics procedures that were needed to be developed on the fly in a very short period of time. The Canadian Space Agency were key in helping us get those done. And we had engineering organizations across the country helping us understand exactly, or helping us talk about what configuration a solar array might be in, talk about things that Scott might see when he got there, talk about all, of course, the risks associated with him working close to that solar array. And the amount of work that we got done in those 4 days is equivalent to months and months of work that we normally would have done pre-flight. And we crammed all the analysis, all the technique development, all the NBL runs, the practice runs in the pool, all of those things into essentially a 3-day span to support that EVA on the 4th day. And that's a testament to all the resources that we can bring to bear on a problem like this, if indeed we need to.
had a number of different tools, all of which were specially insulated. This is one of my favorites. This is called a hockey stick, and this is a tool that I would use if I thought that the solar panel were on its way to contact me. I didn't want any direct contact with the solar panel, because any arcing or direct interface with metal parts in my suit could then ignite inside my 100% oxygen spacesuit environment. So my buddy Doug Wheelock at the base of the array was there as my spotter, and if he saw the solar array going away from me and then starting to accelerate back towards me, he would warn me, and I would get this tool out in front of me so that the ray would pass harmlessly above my head and below my feet. But it was kind of a catch-22. I had to both be in close proximity to the solar array so that I could install these special cufflinks, but I had to keep it at the right distance as well so that it wouldn't touch any of the metal parts of my suit. So I ended up figuring out a way to use 3 tools at once. I had a tool that pulled the solar panel towards me, called a loop pin puller tool, a little hook at the end of it. I had the hockey stick out here in front of me as well, and simultaneously I would poke the cufflink through the hole. One of the challenges of manufacturing in a weightless environment is that things don't settle. Dust doesn't fall to the ground. In fact, it stays pretty much where you generate it, or it'll depart at velocities proportionate to how quickly you cut. And so George Zamka and Peggy Whitson were the 2 crew members who built these things, and there was a lot of concern at the time that particulate aluminum, as they were using tin snips to cut these things into shape, would get in their eyes, be inhaled, and so on. So they, of course, wore personal protective gear, eyewear, and masks, and then had the space station vacuum cleaner at the ready as they were very carefully cutting these into shape. And it was very precise work. Had this been even a few millimeters too broad or too long, I probably would not have been able to get them into the hole. So they did very exacting work, even with the additional overhead of the personal protection. There was a lot of preparatory work before going out on this particular spacewalk. We had to insulate the metal tools that we're going to be working with Kapton insulative tape so that we wouldn't have a conduct path back into the suit. And then also the metal wrist disconnects on my spacesuit had to be wrapped in Kapton tape as well. And as you might imagine, we had a number of video conferences with experts on the ground to review procedures and make sure that we had a very thorough understanding of what we're about to go do.
One of the things that was very impressive about how this activity played out was the creativity and the thinking outside the box that a lot of these organizations did. We had no pre-planned techniques or hardware to repair, of course, a tear of this sort, a tear along this hinge line. And it was very important that we get the array completely deployed so we got the structural stability that we needed. But we needed to make sure that we didn't continue that hinge tear and get what they called a zipper effect with the arrays coming completely apart. So we needed some way to take the load off that damaged hinge while getting the array completely deployed. And it was so impressive what these guys came up with. We've got a console position called the OSO position, which is responsible. It's the Operations Support Officer. They're responsible for all the on-orbit maintenance. So they're the nuts and bolts guys and the tools guys, and they're the real creative thinkers in terms of fixing things that you didn't necessarily think needed to be fixed. And these guys, in concert with their engineering counterparts, came up with this brilliantly simple yet highly effective repair technique that we called cufflinks, using cables and other hardware that was already on orbit, some of it destined to be thrown away because it was support equipment that came up with other hardware. And they designed these very simple cufflinks that could be used to basically span the tear and take the load off that tear when the solar array was completely deployed. So again, looking back at Apollo 13, they had the same. It's interesting. They had the same kind of thought process that they had to do on Apollo 13 to do the carbon dioxide removal. I think the things that our operations support folks on 120 did to affect the solar array repair is very similar, very analogous to what the kind of work they did on Apollo 13. In the Mission Operations Directorate, we have a long and rich history of supporting manned spaceflight, going all the way back to Mercury and Gemini and Apollo. Of course, Chris Kraft was the first flight director here at Johnson Space Center. He essentially imagined and designed the job. He's the reason that the flight director role is executed as it is today. Of course, Chris Kraft went on to be center director at Johnson Space Center. But everything we do, all our philosophies, all our tough and competent creed, our core principles, all trace directly back to Chris Kraft, and that attitude just permeates the entire MOD team. Everybody's completely committed on the MOD team to keeping the crew safe, keeping the vehicle safe, and then executing the mission. And I think you really saw the capability of the MOD team in this activity, where we had a significant risk to the assembly sequence. There was, initially nobody knew how we were going to fix it or how we were going to get around this problem. And within 4 days, with the help of all the other parts of the organization, we had that array repaired, and we had the space station in a great configuration to complete the assembly sequence. One of the things that's been very satisfying to me, watching from afar, if you will, was the recent success of the SpaceX Dragon mission. Because before, I was also the lead flight director for STS-134. Prior to that assignment, I was working as the flight director representative to both SpaceX and Orbital as they built up to their cargo flights to the International Space Station. Both very, very capable organizations, great teams, but of course they have a lot to learn about spaceflight, which they recognize. But when I got the 134 assignment, I gave up the SpaceX and the Orbital assignments, but I was very happy to see the success that SpaceX had with their Dragon cargo mission. But what I found especially satisfying was how well the teamwork and the cooperation and the coordination played out during that mission, because there were some challenges in the hours leading up to the actual rendezvous and grapple. And the teams, the flight control team in Houston, led by a station flight director, and the teams in Hawthorne, led by their flight director equivalent, their mission director, and their flight control teams, worked together seamlessly to work through these challenges that they encountered as the mission progressed. And it was gratifying, rewarding, encouraging to see that the lessons learned and that the relationships that these teams at SpaceX and MOD have built over the last years leading up to this mission really came to fruition. I think we can learn a lot from each other, MOD and NASA in general from SpaceX and vice versa. I think MOD has brought a lot to the table in dealing with SpaceX in terms of just all the lessons learned that we have over the years in terms of how to do mission operations, how to make critical decisions, what the procedures and the techniques and the rules are that need to be in place, and then ultimately how critical that communication is in real time to be successful.
The flight started off as a very different flight. We had 5 EVAs planned, and the team had worked very, very hard on those 5 EVAs. And then once we got in and we completed the first 3 EVAs, we were attacking completely different 4th EVA for the solar array rotary joint, and then that went by the wayside. And also we had the two of the planned EVAs, and those went by the wayside, including a shuttle repair techniques EVA that we had been looking forward to for quite some time. So really the team was already tired maybe, you could have had a low morale as a result of loss of 3 of the EVAs. Of course, knowing that you were going to go do a repair is exciting, but there could have been low morale, but there absolutely was not. And I think in this particular case, our EVA team is generally pretty upbeat. Something breaks, we go fix it. That's what EVA is about. But in this case, we had a really big risk trade. It was a really big risk to the station program, to our crew, to have this torn array. We didn't want to undock, and we didn't want to redock in this particular configuration. So folks were really motivated and really driven to make this happen. Everyone was very positive, and I think that's one of the key takeaways is you take a really big problem, this big torn array, and you break it down into small chunks and make it doable. Can we avoid risk of electrocution? Can we avoid risk of molten metal? And you break it down into these small pieces, then it becomes something that's surmountable. And I think that the team stayed very positive throughout the entire experience, which was really critically important. We didn't have a lot of naysayers, and you can't do that. Our team was very, very focused on making it happen. And then if we had run into a safety roadblock or something, then of course we would have taken a step back. But we went in with a really very positive outlook, and the team did a fantastic job pulling it all together in the end. Again, my name is Dina Contella, and I am now a flight director, and if you would like to contact me, you certainly can. I'm in the flight director's office at the Johnson Space Center. And also, of course, we keep our resident EVA knowledge in Mission Operations Directorate in the EVA branch. So folks would be available there to also answer questions.
One of my key personal takeaways from this mission is just how capable both the operations team and the larger team, including engineering and safety, is, and what they're capable of doing when presented with such a significant problem. And it's we do a tremendous amount of work in mission operations in MOD to prepare for the nominal mission, the normal mission. And then we look at a number of contingency scenarios. But I think what 120 demonstrates is that preparation really trains the team to address just about anything that you can throw at it. Because you're so familiar with the normal timelines, because you're so familiar with the contingencies that you work through, you've got an intimate understanding of the hardware, of the software. You've got the relationships with both the crew on orbit and your flight control team. When you have that well-trained team, that commitment to excellence, there's very little that we can't overcome in terms of surprises during a mission. If you do have any other questions about the STS-120 mission specifically, or real-time operations in general, other station assembly missions, other shuttle assembly missions, you can certainly contact me in the flight director office, or you can contact one of my colleagues in the office.
One of my mentors in spacewalking, also a physician astronaut and a spacewalker, is Dr. Story Musgrave. And one of my favorite quotes from Story is, the only thing expected in EVA is the unexpected. And what he meant by that is just be prepared for things to turn south. This is a very unusual environment, huge temperature extremes, the vacuum of space. Things just don't behave the same way in space as they do here on Earth. So be prepared for curveballs, because they almost invariably happen. And certainly in all of my 7 spacewalks, there were little curves along the path that we had to deal with. The solar array repair, of course, was the largest chink in the road, but every spacewalk that you'll ever watch has something that is a little bit out of the norm. The way that we choreograph the spacewalk on the ground, it doesn't always translate exactly the way we'd envision. So the way I prepare for my spacewalks, and based on my advice from Story, is to really get down and understand how the spacecraft and the subsystems work, to take out the wiring diagrams and and understand how the electrons and the ones and zeros and the photons and so on flow, trying to understand how it should work in the normal sense, how things might break, and then how you might fix things if things really went far afield. We do our best to develop malfunction procedures for the things that are most likely to fail, but it's very easy to get down 2 or 3 failures deep and not have a fighting chance if you haven't thought about it. And so that was always my approach to the space flight training, and I think it really helped And I would suggest that same sort of approach for not just the crew members, but of course the engineers and flight controllers of the future. I think when thinking about spacecraft of the future, we can't assure reliability ad infinitum. So thinking about maintenance for the long haul is very key. And one of the great lessons that we learned from initially the Hubble Space Telescope and subsequently aboard the International Space Station is designing things to have human touch in the future, to have the provisions to get a crew member out there, to have a fighting chance to repair things. And we've seen, certainly with the Hubble, really dramatic repairs that have taken place there on boxes that were never meant to be touched, without captive fasteners and deep inside the bowels of the telescope, where really complex types of repairs have taken place only because the basic provisions for repair and maintenance were installed from the get-go. And so I do worry about the Webb telescope being, at least the way we currently envision it, beyond the reach of human hands. But certainly as we prepare for future human missions to places beyond Earth orbit, we need to really make sure that at least the ability to get out to have a fighting chance to repair things is built in from the ground up. I think my medical training and background really did prepare me well, not just for the solar array repair, but EVA in general. It's taking a kind of a surgeon's approach to being prepared, making sure that you have the right work site, that you are smooth and controlled, and you treat the patient. In this case, it was a solar array panel with respect. So this is not a task for someone who's rushing to get the job done. You don't want to be ham-fisted with this at all. It required a lot of precision and slow and deliberate motion. But I think the majority of astronauts who come through the program have great fine motor skills, either from aviation or medicine or rebuilding cars, growing up working with their dad, what have you. That's sort of how I think developed my mechanical skills, building furniture and working on cars as a kid. But those sorts of experiences earlier in life, working with tools, problem solving, thinking in 3 dimensions, are the same sorts of things that are required for spacewalking. One of my key takeaways from the STS-120 mission is the fact that our broad training and the wealth of preparation that the mission control and technical teams put into every mission gives us a lot of reserve. We like to stay between the lines and follow the straight and narrow, but there are times when we need to deviate to get the job done. And I certainly felt that I had the tools in my technical ability and knowledge base, and I had confidence in my teammates, both on orbit and in mission control, that we could go out and do a challenging task such as this. And so that's the take home for me, that we have tremendous potential to do extremely challenging things in space when the bar is set for us a little bit higher than we'd like. So if you have any additional questions on anything that I've discussed here today, feel free to reach out to me through my website. It's www.parazynski.com, Parazynski.